Hello everyone. In this video and three other videos I prepared, I'm going to talk about different aspects of differential equation solvers, and we are talking about numerical solutions. So in one of my videos under the playlist mathematics, you have seen me talking about numerical solution of ordinary differential equations, and I talk about the Euler method, the improved Euler method, and the Runge-Kutta fourth order. So I'm talking about this video here. And there are so many aspects of it that need to be further explained. One of them is in solvers of ordinary differential equations, there are three categories of solvers. One group we call them explicit methods, the other groups we call them implicit methods, and there is a group that is basically a combination of explicit implicit, which we call them implicit explicit methods, or IMEX. So let's see what they are. That is what I want to explain in this short video. So if I have a differential equation of form y prime equal f of y of t, and this is of course subjected to some initial condition, then if the update equation from which we can find the values of the function or the solution at different time points is directly given, like y at t plus delta t, the next y, the y at the next time step, equals some direct function h of the current y of t, or it could be y of t and t. Okay, so this t also could be implicitly mentioned in h in addition to y, but all you need is to bring in the previous time step and the previous y value to get the next y value, and it's just a direct plug and play. So it's very easy and very fast update, which we call them the explicit method. Now sometimes the next value of y is not directly given as a clear function h of y. It's actually an implicit function like this, where g of y and y of t plus delta t, again there could be some t as well here, equals 0. So in this case y of t plus delta t is not directly solved for in terms of y and t, and it's a function of all of them which is like equal to 0. And then in this case, if you want to find y of t plus delta t, you have to do a root finding problem, right? So this is clearly a root finding problem, and sometimes there is an analytic solution depending on the g function, sometimes there is not, so you have to solve it numerically. Okay, so in order to clarify that, let's look at this simple ODE, y prime equals, or y dot equals negative y squared, where t is between 0 to a, and it's subjected to initial condition y of 0 equal 1. So my first t is at 0, and then the next t, which is at delta t, basically the next time point, which is at 0 plus delta t, or delta t, is at a over n, and a here is the entire range divided by the number of step points. So you can say that my sample points tk in general is a over n times k, okay? K times delta t, right? So this is equal to t0 plus what? Plus k times delta t, and t0 is 0 in this case, and k times delta t becomes ak over n, right? So now, if we use the forward Euler formula or forward finite difference to calculate this or approximate this dy over dt, we can say that this dy over dt at step k is approximated by forward finite difference, which is y at k plus 1 minus yk divided by delta t. Now, if this y prime equals negative y squared, so in this case negative yk squared, then the only unknown here is the y at the next iteration given the y at this iteration and the known delta t. So if you multiply both sides by delta t and take the y to the other side, you see that y of k plus 1 becomes yk minus delta t times yk squared. So this is clearly what? An implicit function of y of k, right? And there is no t in this case. Okay, delta t is just a constant. So you see, all I need is to start from y of 0, right? So if I plug in basically k of 0, then here from here you see that y of 1 equals, for instance, what? Y of 0 minus delta t times y of 0 squared. And let's say delta t is, for instance, 0.01. So if you plug in y of 0, which is 1, you get 1 minus 0.01, so you get 0.99. And then you keep going, right? Then you plug in y of 1, you get y of 2, and so on and so forth. It's just direct plug and play. Now, on the other hand, if we use the backward Euler formula for approximation, then this y prime is approximated by y of k plus 1 minus y of k over delta t, okay? This is equal to negative y at k plus 1 squared, because now we are calculating everything at k plus 1 based on k. And if in this case I cross multiply and sort it out, you see now the equation I have is not y of k directly as a function of y, because it appears in two different places. So if I bring this to this side and set it equal to 0, now I can say what? A g function of y of k plus 1 and y of k equals 0. And the goal is to treat it like a root finding function. Here I want to consider this y of k as an unknown, right? So like, for instance, x. So this is the linear term. This is like a times x squared. And this is like, for instance, that constant c. So this is like a quadratic equation, basically, where the unknown is yk plus 1. And in this case, it's solvable analytically. Yk plus 1 becomes what? This solution of the quadratic equation. Now, most of the time, it's not that simple, okay? For instance, if this guy was what? This guy was cubed instead of that, then here you would have cube, and the analytic solution here, although still exists, it's quite a bit harder to find it, okay? Or if this function was a little bit more complicated, right? So you had some further extra terms and so on, then, or maybe, for instance, I had something like negative sine of yk plus 1, then this equation becomes what? Becomes basically delta t times sine of yk plus 1 plus yk plus 1 equals yk, and now there is absolutely no analytic solution. So you have to definitely solve this numerically. And that extra numerical solution, or even this analytic solution, that is some extra step that you need to do. So these implicit methods basically require some extra computation to solve this equation number 3, okay? And as I said, sometimes that numerical solution is taking more time. So why do we use them? If we can always get along with using an explicit formula, why should we ever use an implicit one? The reason is, as we'll see in one of my upcoming videos in the next couple of days, these are useful when the equations, the ODEs we want to solve, are called stiff. Okay, what is a stiff ODE? We're going to see that. We're going to see examples of that, and we'll see that implicit solvers are useful when what? When they are used with stiff methods, because explicit ones, if they want to solve stiff problems, stiff ODEs, they need very, very small time steps to keep the error bounded, and that makes them very slow to use or sometimes impossible to use. But implicit methods actually allow to solve for stiff ODEs, okay? And they take a lot, basically less computation, okay? So we'll get to this. As I said, this is the topic of one of my upcoming videos. So just know that implicit solvers, they have their own applications. Just wanted to distinguish between implicit and explicit. And as I said, there is a last category, which is a mix of the two. We call it implicit-explicit method, or IMEX, where y of t plus t, the next y value, is what? is basically a combination of an explicit function of yt and an implicit version. Okay, and to make it easy to solve for y of t plus t, what we do is we make sure that this f function is what? We make it that this implicit function chosen to be linear. If we make this linear, and this is like a times y at t plus delta t, then we can take it to the other side and directly solve for y of t plus delta t. But the explicit part, this g, can be as nonlinear as it wants because we don't care. We just plug y of t in it and it's just plug and play. Okay, this is this implicit part that makes it hard, but if we have it linear, then it could be a lot easier to do. For instance, let's look at this ODE dy over dt, or y dot equals y minus y squared. Again, t is in the same range. Now what we do is we use the forward Euler formula again. Okay, y of k plus 1 minus y of k over delta t, set it equal to the right hand side. Now pay attention to what we do on the right hand side. Instead of calculating both of these y's at the current k, we use the linear portion for the implicit part, and we use that nonlinear portion for the explicit part. You see, this nonlinear part, we apply the previous or the current iteration value, but this linear part, we use what? We use the next value, which is the unknown. And now, if you set these two to be equal, this yk plus 1, which is the unknown, is only appearing as a linear term, so you should be able to easily what? Solve for it. All you need to do is to multiply both sides by a delta t. So if you do that, you get this. And then what you need to do is to bring this term to this side and to take this -1 to the other side. If you do so, you'll get what? You'll get y of k plus 1 times 1 minus delta t, if you factor it out, is equal to, on the other side, you have yk 1 minus delta t times yk. If you factor out the yk, and then all you need is to divide both sides by this term, which is exactly this one. So if we want to know why we have these IMEX methods, the answer is if we are dealing with stiff equations, as I mentioned earlier, and we want to solve for them, yet we want to avoid this root finding problem, okay, which is a time-consuming thing. This implicit explicit methods, they are trying to combine. They are trying to bring in the implicit parts, so we still can use them for solving stiff ODEs, yet they do not really need much of a root finding in a numerical manner, because this implicit part is linear, so we can turn that numerical root finding into a simple analytic formula like that. Okay, so they kind of have the advantage of the explicit and implicit methods at the same time, being able to use them with the stiff at the same time, not requiring a separate numerical root finding part. So hopefully this simple video was useful to you, and as I said, stay tuned. I have 3 more videos coming. The next one is we talk about the errors and the error tolerances that we have in solving differential equations, including the command ODE set in MATLAB. So we're going to talk about local and relative and absolute errors, okay, which are important. And then we're going to talk about basically the variable size, step size ODE solvers, because most of the thing that you have seen, including in my video on my channel, is about a fixed step size, but in MATLAB, if you have seen, most of the solvers are variable or adaptive step size. And finally, once we have all these prerequisites, we go and talk about what stiff ODEs, A and L stability. So stay tuned, you're going to see more videos. Thank you. See you in the next lecture.